Recording starting. Okay. Okay. So today is the first class for the new topic, which is Newton's laws of motion and friction. These are two separate things, but we will usually right now we will combine the two things at the by the end of the class. Okay. So everything that you have learned before, we learned about how to resolve forces. We have learned about the kinematics, the motion of any object, the velocity and acceleration and the speed time from everything. Now all of these things combined together, we call it dynamics. Dynamics is forces and its effects. What happens when a force is being applied, or what are the resultant things and everything that can happen. Okay, so Newton's laws of motion, we have three laws of motion. I will not write all of them down. Three laws of motion. We should have the understanding. They won't ask you for the definition for the laws of motion, Newton's, but you should have the knowledge and understanding behind the laws of motion. First one is that any object will continue its state of rest or motion unless acted upon by an imbalanced force. This means that if something is at rest, for example, there is a ball resting on this table and it is at rest. Okay, it is at rest. The velocity is zero. So it will be always at rest unless there is a wind that is flowing around it, unless I push the ball, and unless someone kicks the ball, unless an imbalanced force acts upon it. Right now, this ball is under equilibrium. It is in equilibrium because all of the forces, they are equaling each other out, and the moments are also equaled out. This is in equilibrium. We learned about equilibrium is what? The sum of forces, the resultant force is equals to zero, right? Fr is equals to zero. Resultant force is zero. And when an external force, when an imbalanced force, imbalance means that there is now acting a force which has not been balanced by another force. And when that force acts on this, then definitely this ball won't stay at rest. It will start moving with a certain acceleration or velocity or anything. It will now cover some displacement as well. So this is the first law, that anything which is at rest or at constant motion velocity, okay, it will continue its state of rest or motion unless acted upon by an imbalanced force. The second one is more important. The second one interpretation, the formula that we can derive from the second one is F is equals to ma, that the resultant force is equals to the mass of the object multiplied by its acceleration. And resultant force and acceleration both will be in the same direction, both in same direction. For example, if right now the ball was in equilibrium and someone kicks the ball horizontally, he or she has applied a horizontal force of, let's suppose, 10 newton. So definitely the ball would start to move in this direction, to the rightward, isn't it, in the direction of the resultant force, because this is the resultant force. Overall force on the ball is now this 10 newton. So the acceleration or the velocity of the object would be in the same direction as the force. Okay, this is the rule, that the acceleration will always be produced in the same direction as the force, as the resultant force on that object. Okay, this is important, and it is equal to the mass times the acceleration of that object. It would always produce acceleration. So whenever your resultant force is not equal to zero, then your acceleration is happening, is present, or is there, or what do we say, is also not zero, because mass cannot be zero, isn't it? Mass will always have a value. Mass cannot be zero kg. There is always a body with a certain mass, 5 kg or 2.5 kg or 0.5 kg, 1 kg. And if there if your acceleration And mass is a constant, because mass is a constant. Yes, this is a better word. Mass is constant. Mass cannot change. So if this means if you have a resultant force, and if this is not zero and it is a constant, then definitely there would be acceleration happening, acceleration with the object. Okay, and if your resultant force is zero, this means that acceleration would be zero, because mass is again always present. Mass is a constant. Mass will never become zero. So this means that if your acceleration is zero, sorry, resultant force is zero, then acceleration is zero. And acceleration can be zero in two cases. Acceleration can be zero when your velocity is zero, or when your velocity is constant. Okay, so that's why we have two definitions or two types of equilibrium. We have a static equilibrium and we have dynamic equilibrium. Static equilibrium, and we have dynamic equilibrium. Equilibrium. Static equilibrium means that the object is at rest. Velocity is zero, definitely then acceleration would also be zero, and definitely then the resultant force would also be zero, because mass cannot be zero. Mass will always be there. So if something is at rest, its velocity is zero, then definitely acceleration, it is not increasing or decreasing. The velocity is not increasing or decreasing. So acceleration is also zero. And if acceleration is zero, then resultant force is also zero. Dynamic equilibrium is then if your object is at constant velocity. When it is constant velocity, then definitely acceleration is zero, and definitely the resultant force would also be equal to zero. So let's suppose if there's a car which is traveling at a constant speed. Let's suppose the car is traveling at 30 meter per second. So this means that that car, the sum of the forces is zero, because constant speed means acceleration is zero, and if acceleration is zero, then due to this formula, resultant force will be zero. So resultant force means that the sum of the forces on that car would be zero. This is something very, very important to understand. Okay, so this is one of the few things. If we get to some more examples of equilibrium, let's suppose, and one more thing. Okay, one of these things is this. Okay, static equilibrium, dynamic equilibrium. Now we know about this. So there is always, whenever resultant force is zero or equilibrium, then sum of forces would be zero. So always there is a counter affecting force. Always a counter effect producing force somewhere. And the most common ones we would learn is the normal contact force, normal contact force, and friction. Okay, for example, right now this is a table. This is a table, and there is a book lying on this table like this. Okay, the book is of, let's suppose, I don't know, 0.2 kg. But right now the book is at rest. The book is at rest. So definitely on this book right now, how many forces are being applied? Can anyone suggest how many forces are being applied on this book, in this system?
Two,
What are they?
the normal contact force and the gravitational force.
Yes, good. So gravity of the book would be pulling it downward, which would be weight is equals to mg, the basic thing, which would be mass times acceleration, which is 10, so 2 Newton. And right now we know that this book is at rest. So this means that there is a force which is countering this weight force of the book, which is acting definitely directly upwards from the point of contact of the book to the table. And this would be how much? This would be normal contact force, R. We call it most probably R or N, whatever that you want to call it. Normal contact force, which would be the same as the weight. Because we know this object is at rest, so sum of forces would be zero. There is no horizontal forces. So definitely the weight would be equaling the normal contact force. Normal contact force. And that's why this object is right now at rest. For example now, if I start to pull this object, this book right now with at least, I think, 0.2 Newton as well, if I pull it upwards, then the resultant force would be upwards now, because these two forces are cancelling each other out, and now there is an external force which is pulling it upwards, which is 0.2 Newton, which I have applied over here. And because of the 0.2 Newton, the book would start to accelerate upwards, because now there is a resultant force of 0.2 Newtons. There is this extra force which has not been neutralized by anything else. Okay, so now the book would start moving upwards in the direction of the resultant force. It would start accelerating. Do you get it or not? Okay, this concept is very important, so that you understand how many forces are applying and how they are interacting, which force is cancelling out which force, and how to find the normal force, and everything is very important. Okay, let's do another example. A very good example is of a car. Okay, so let's suppose the car is moving. The car, sorry, what do we say? Yes, the velocity of the car is, let's suppose, 40 meter per second. And acceleration of the car is zero. The car is right now moving at constant velocity. Okay, the forward force, the driving force of the car's engine, let's suppose it is 1000 Newton. Now there are right now two types of resistive forces that are acting on it. That are trying to, what do you say, counter the driving force of the car. One of them is the friction with the road, and the other one would be the friction due to air resistance, or you can say. Right now we know there are two more forces that are acting on it, on this car. Can anyone identify? There are two more forces right now that are interacting with each other on this car. Anyone?
Sir, downwards and upward force,
Yes, and what are they?
gravity and contact force.
Yes, good. They won't tell you in the question always. Okay, so this thing you have to identify yourself. You have to understand the situation. You have to analyze what forces are being applied, and then which of them are interacting with each other. So there are two more forces. Good. This would be the weight of the car and the normal reaction force on these two tires. Normal reaction force on the two tires. So right now, because definitely the car is not going to jump up and down. So the resultant force in the vertical direction is zero, because the car is not moving in the up and down direction. The acceleration is zero in the up and down direction. So resultant force in the vertical direction is zero. So this means that the weight of the car is equals to the normal reaction force at 1 plus the normal reaction force at tire 2. Okay, 1 and 2. Let's call it 1 and 2. Okay, and right now in the horizontal direction as well, we know that the acceleration is zero. Sorry. If the acceleration is 0, then definitely the resultant force would also be equal to 0. So this means that the driving force of the car is being cancelled out by the air resistance plus the friction with the road. Okay, this is the situation right now. And because of this situation, the car is right now traveling with a constant speed with resultant force 0. Let's suppose I'm giving you a situation. Let's see who can answer. Right now, this car is traveling with this situation. Okay, this is the current situation. After 1 second, there's a very what do you say, strong gust of wind backwards. Extra gust, you can say a very strong wind that blew and then pushed this car backwards. So what would happen to the car? What would happen to the car? Nova, Nadia, anyone? Murtaza? No one? Any suggestions? Anything? Can you hear me or not? आवाज आ रही है?
Yes, sir, we can.
हाँ तो no idea. Okay, so let me give you what would happen. So let's suppose right now this was the current thing and then something extra, and a strong wind blew backward. So definitely this would also apply extra force, air resistance, force of the air backwards. So initially this driving force was being cancelled out by the friction of the air and the friction due to the road. Now there is this extra force that is acting. This would be the resultant force. The extra force, the overall force would be this force backside of the car, which would be negative, right? It is going to the left side. So definitely the acceleration, this force would now generate acceleration in the opposite direction and the negative side. So what would happen? The car's velocity, acceleration is now negative, and the velocity would start to decrease. The velocity would decrease as long as there is a strong wind, and as long as there is this negative acceleration, the velocity would keep on decreasing unless this wind is has settled, and now this is the same situation again. Okay, if someone drives a bike, they must know about it. Whenever you feel a very strong gust of air, you feel like that your car is trying to exert more pressure. The car is trying to is not picking up speed very fast, or it's slowing down again. Or if someone drives a bicycle, he or she can also must have also what do you say, experienced this thing, isn't it? Anyone or no one? You have to apply an extra force, exert an extra force, so that you can cancel out that air as well and then move on forward. Okay, so this for these forces are everywhere. Analyze these things. Where are these being applied? Whenever you walk and then you feel a very strong air coming in, so you have to exert more pressure, so that you have to cancel out the force that the air is pushing you backward. So that's why you have to exert more, and then your velocity also decreases, isn't it? Slightly. No or yes? Do you get it or not?
Yes, sir.
Yes.
So you have to understand the situation, not just read the question start off directly. Understand yourself as well. What can happen? What will happen? Okay, this is happening. This is happening. The car is trying to what do you say? Move up a hill. So definitely it would be difficult for it. Okay, so these things we have to visualize the situation that the question will give you, and then try to solve it. Okay, not just by directly using the formula and everything. These are things are very logical, very physical. You can analyze the things happening in your mind. Okay, so try to visualize the things, and that will be more interesting as well to understand, easier to understand. Okay, so now we know about the normal contact force, about the friction force. These are just reaction forces which help us to help, not what do you say, These are also present. Normal contact force, friction force. Now, for example, now moving on to the how the questions come in, how we work things around here. For example, this is the block. Okay, and the weight mass is equals to 2 kg. Okay, and then there is this force acting like this at an angle of 40 degrees. This is a force of 30 Newton. Find the normal contact force. Contact force or normal force, the same thing. Normal force exerted by the ground. This is the ground. Okay, right now forget about the horizontal sum of forces. Okay, forget about the horizontal part. We have to analyze what is the normal contact force right now. Okay, this is a very important thing. Forget about the horizontal part. We work on right now on this situation the vertical part, because normal contact force, the weight and everything is vertical. So weight is always acting vertically downward. Weight is always vertically downward. 2 times 10 Newton. And if we break this 30 Newton force into its component, one would be its horizontal component, which would be 30 cos 40. Right? This is what we have done. The component which is adjacent to the angle is cos. And this one would be 30 sine 40. And we know that these two are the forces which are acting downwards. So there would be definitely one more force which would be cancelling out these two forces, which would be acting upwards. Because this object is not going to move up and down. Okay, this is just standing over. Sorry, it's just not moving vertically. So this is the normal contact force. This would be present. So right now, this equation which becomes right now is that the normal contact is equals to the sum of all downward forces. So 2 times 10 plus 30 sine 40. This is the answer. This is the normal contact force right now on that is acting on this block, which is 42.35 42.35 Newton. Okay, do you get it? Any questions? Okay, I think it's all good. Let's do one more example. Hmm. Okay. Okay, this is something interesting. Okay. Okay, the question is telling that the object is in equilibrium. Find the normal force and the F max. F max means the maximum friction force. Okay, frictional force. F max This is something that we would use for this friction, F max. Okay, normal force and F max. Okay, so first of all, again, it has told us that the object is in equilibrium, so the sum of horizontal forces would be 0 and the sum of vertical forces would be 0. You identify all of the forces. Weight, definitely it has a mass, so there would be a weight acting downward, which would be mg. So 2.5 times 10. And you break it down into its components. So this would become 25 cos 20. And this would become 25 sine 20. Okay. Okay. So now if you equate the horizontal forces, we can see there's only one force to the right side and one force to the left side. So this means that F max would be definitely equal to the rightward force, which is 25 cos 20. And vertically, if we see, there is a force upwards, there is a force downwards, and there would be definitely a force which would be exerted by the ground, which is the normal contact force, which would be upwards. We don't know that. That's what they are asking us. Normal contact force. So right now the equation becomes what? Normal contact force plus 25 sine 20 is equals to 25, the weight of the object. So normal contact force is equals to 25 minus 25 sine 20, which is how much? 16.4 Newton. This is the normal contact force, and 25 cos 20 is 23.5. This is the frictional force. Over here, I think I have used the calculator wrong. It was in degree, sorry, that for mode which we call radian mode. This is the correct answer, 39.28 or 3. Okay, this is how you would resolve forces now in a very, what do you say, application based question. In the previous chapter, you just had arrows, you just had the force vectors, that's it. Now they are related to a situation. Now there's a box, there's a car, there's a train, there's something else, there's a plane, anything. Okay, so this is how you would relate the weight and the normal contact force, friction. Okay, any questions? Ask now. Ask. Copy this down. If you have any questions, ask. Now, these were situations in level ground. Right now, the ground is leveled, horizontal. When you have inclined ground, when you have inclined planes, that is something. This becomes more interesting. Inclined planes. So you must have also experienced yourself whenever you are climbing up the stairs or whenever your car is trying to go up a hill, it becomes difficult for the car and for you to climb something. Why is it? Anyone? I need the scientific reason behind it. Why does it feel that you have to exert more force when you're trying to climb something, when you're trying to go upwards, trying to go through a inclined surface? Anyone?
You're going against gravity, so it's
You can.
harder.
Going against the gravity needs something better.
Yeah, like the opposite way.
This is still not okay. It's going against the gravity, yes, but still when you're walking, you are walking against the gravity. You are that, and on that situation as well, you're walking against the gravity. But when you are trying to go up, then it's something else.
Sir, is it because the force divides into separate horizontal and vertical?
You are very close. You are very close. You are very close. Whenever you are, uh, whenever there's something like this, there's an inclined plane, okay, and there is an object. Why does this object will start to slip down? Anyone? Without you doing anything. Is there any, is there is no resultant force, there is no external force acting on it. But still you will see that this block would start to go down. Isn't it? Because the force right now, the when you had a level ground, your weight was only being countered by the normal force, which is exactly opposite to the weight. But now your weight is still downwards, but the force which is countering this, it's not vertically upwards. The normal contact force is this weight component is now being distributed. One force of the weight is now being distributed along the plane, and one of it is being divided into perpendicular to the plane. This is the weight component perpendicular to the plane and the weight component along the plane. So without any external force acting on this body, this can start going down because the weight is still vertically downward, but the effect of this weight is now divided into two parts. One of it is the weight component along the plane, and this is the weight component perpendicular to the plane. And if there is no force that is countering this force, then definitely it would start go down. And there is a normal contact force like this, which is directly opposite to the weight component perpendicular to the plane. Normal contact force is always perpendicular to the surface. This is always perpendicular to the surface. Right, look, this one is also perpendicular to the surface. So this weight component perpendicular to plane is being cancelled out by the normal contact force. And if this force is not being cancelled out by anything else, then definitely there is a resultant force in this direction. And whenever there is a resultant force, the object has acceleration and it will start to move down. Isn't it? ऐसा ही होता नहीं होता? Do you get it or not?
Yes, sir.
So this is the background. This is why. So whenever your car is trying to go up a plane, so car has to overcome the friction. That's it. The friction that was over here in this situation, this friction is the same over here as well. The same friction. But now the car has also to what do we say this? Also to counter the weight effect, its own weight effect. So when the car is moving in like this, it has to overcome the friction which is acting out downward, and it has also to overcome the weight component of the car's mass. So now this is doubled. So that's why more force is required for you as well, for the car as well. Isn't it? So that's why it is more difficult to move large vehicles, trolleys and tractors and trucks, and they are much more difficult to be there to travel inclined surface because their mass is so much that the weight component becomes very big, and that's why the engine has to work very hard so that it can cancel out the weight component as well along the plane. So extra force, extra effect has to be applied. The same case is when you're trying to go down. If you're walking downstairs, then it becomes easier for you to travel because you don't need to make additional efforts. The weight component is actually helping you to move down. Weight component is down and it is helping you move down, so it becomes easier for the car as well, for you as well to move down. So this weight component is very important. Okay. Okay. Okay, this is a lot for today's class. There's should we continue? Okay, let's do one thing more, because this is, I know already a lot of things to right now understand, very logical things. Okay, this is your level ground, and let's suppose this is your inclined plane, and there is an object like this. Okay, this is an object. Now I will explain to you how can you calculate the weight components. This is the angle of inclination, and we know that the weight of this box would always be vertically downwards. This is the weight, and if you want to break it down into its component, horizontal and sorry, along the plane and perpendicular to the plane, they would be like this. This would be the component perpendicular to the plane, and this would be the component along the plane, right? Sorry, my diagram is not that good. I hope you can understand this. So this is the, sorry, this is the component perpendicular to the plane, and this is the component along the plane, and this is the resultant weight component. Now if you see this, this is forming a 90-degree. Okay, and definitely this would also be 90-degree. Okay, this would be how much? 90 minus theta, right? 180 minus 90 minus theta. This would be 90 minus theta. And if you apply the z property, look, this would also be 90 minus theta. And if this is 90 minus theta, then this would be how much? This would be theta. 180 minus 90 minus 90 minus theta. This would give you theta. This would be 180 minus 90 minus 90 minus theta. So if you solve this, this would become 180 minus 180 and plus theta. So plus theta. Isn't it? Do you get it or not?
Yes, sir.
Nuba, Murtaza, and Nadia.
Yes, sir.
Okay,
Yeah,
good.
got it.
Now, using this thing, we can now find the components. Okay, sorry. Let me erase now. The things that are relevant to us is only this part. Okay, we know that this is mg, right? This is the weight, and this is the component which is adjacent to the weight. So this would be mg cos theta, and this would be a component which is opposite to the angle. So this would be mg sin theta. So now you have to memorize this, that whatever your angle of inclination is, the weight component along the plane would always be mg sin theta. Let me repeat this. Whatever your angle of inclination is, the weight component along the plane would always be mg sin theta. So if I draw this thing again, this would be the weight component along the plane, mg sin theta, and this would be the vertical component, sorry, perpendicular component to the plane, This is mg cos theta. Now this is something that you would use again and again and again and again and again without using this background knowledge. Okay, this was just for your explanation. How are we solving the angles? Okay, this is the thing important. The weight component along the plane, weight component perpendicular to the plane. Okay, copy this down if you want to understand the background as well. You can copy this down as well. And I think that is it for today's class, because this is more than enough. Try to review these things again. This was a very important class. You learned about normal contact force, you learned about friction and how do they interact, and what situation occur in what condition, what would happen, and if it is inclined or horizontal plane, how would you find normal contact force. And so this was a very important class. Okay, I'm stopping the recording of the class. Okay.